Let's look at voltage drop in action. Voltage drop is the loss of electrical pressure as current moves through wire and connections. Every conductor has some resistance. That resistance converts electrical energy into heat, causing a voltage drop. The longer the wire run, or the smaller the wire, the more voltage you lose. Less voltage at the end of the circuit means less available power for the devices. Think of voltage like water pressure. The farther it travels through the pipe, the more pressure you lose along the way. Here's a simple example. 24-volt power supply, a device 200 feet away. Wire resistance is 2 ohms, round trip, and based on 18 gauge copper. That's out on one wire, back on the other, round trip. Current draw, 0.5 amp. So voltage drop equals current times resistance, which is 0.5 amp times 2 ohms equals 1 volt lost. Voltage at the device is about 23 volts, as opposed to 24 volts at the beginning of the circuit. 1 volt isn't much, but stretch that wire longer, add more devices, or let the supply sag, and you're below the safe range. Many 24-volt fire alarm devices stop working reliably below about 16 or 18 volts. Always verify manufacturer specifications. Voltage changes along the wire. Same circuit, same wire, different voltage at different points. At the panel, you might measure 24 volts. Midway in the run, about 20 volts. At the last device, you might see about 16 or 18 volts. Devices near the panel may operate normally. Devices near the end may receive too little voltage to activate. Voltage drop isn't evenly felt. The farthest devices suffer first. The last device in line tells the truth about your circuit. Let's talk about Ohm's law in a wire. Now let's look at that same example through Ohm's law. 24-volt panel output feeding a device 200 feet away on 18 gauge wire. Wire resistance about 2 ohms round trip. The device draws a 0.5 amp under load. Voltage drop is current times resistance, or 0.5 amp times 2 ohms equals 1 volt. Device now sees 23 volts, not 24 volts. Every foot of wire adds a little resistance. The farther the run, the lower the voltage at the load. The end-of-line resistor example. Ohm's law in standby current. 24-volt panel, 4.7 k ohm end-of-line resistor. Current equals voltage divided by resistance, or 24 volts divided by 4,700 ohms equals 5 milliamps. That small current lets the panel monitor the circuit without tripping an alarm or showing a trouble. The panel primarily monitors current flow, not the resistor. The wrong value can appear healthy for years until the age or heat shifts tolerance and a trouble finally shows up. When resistance drops too low, resistance near 0 ohms causes current to spike. In theory, 24 volts divided by 0.1 ohm equals 240 amps. That's enough to trip protection instantly. We don't normally see that in fire alarm because most of our circuits are power limited or current limited by design. Be careful with batteries. Some can deliver hundreds of amps and may not have external fuse or breaker protection. A shorted battery can start a fire. It can melt insulation and overheat wires until they glow red hot. If current jumps, heat follows. Ohm's law always wins. This is a real-world lesson from my younger days. Early in my career, I shorted a wire inside my car. It overheated instantly and burned my hand before I could pull it loose. Years later, loose fire alarm batteries shorted on a table and filled a room with smoke fast enough to trip a detector and dispatch the fire department. These incidents taught me a simple rule. Batteries can deliver enormous current. Treat them with respect. Low voltage can keep strobes from flashing or horns from sounding. End-of-line devices that don't activate are often victims of voltage drop. Compare panel voltage to the last voltage. A few volts difference is a clue. Long runs, small gauge wire, or loose terminals increase the loss. When devices at the end of a circuit fail to activate, don't assume bad wiring. Your meter can prove it. Measure it under load. Resistance depends on the wire size and length. Manufacturers list resistance per foot on data sheets. Double it for a round trip. Longer wire equals higher resistance, more drop. Shorter runs or larger wire keep the voltage up. Always figure the complete path, out and back. Half the math gives you half the truth. How to reduce voltage drop. Shorten runs when possible. Use larger gauge wire for long runs. Split loads across circuits to cut current draw. Tighten all terminals. Loose equals loss. Check total current before you size the wire. You can't remove resistance, but you can make its job harder. Give the electrons a wider highway and cleaner connections. Voltage drop is the hidden load in the line. Resistance steals voltage as heat. Less voltage means less performance. Keep the push strong. Keep the path solid.